Good day. Today our topic is all about soil water. Soil water is another soil physical property that is very important to study when you are in the field of agriculture. Water content is one of the most variable characteristics of the soil. The soil acts as a reservoir for water, making it available for plants as it is needed. Soil water is part of the global hydrological cycle, which shows how water that falls as precipitation returns to the atmosphere through transpiration and evaporation. On a local scale, how the soil stores water is of great importance in terms of crop production and the vitality of the land. Water affects soil formation, structure, stability, and erosion. Water can also cause soil particles to swell and shrink, adhere to each other, and form structural aggregates. Water alters the soil profile by dissolving and redepositing minerals, often at lower levels. It leaves the soil sterile in case of extreme rainfall and drainage. Water is essential to plants for four reasons. First, it constitutes 85 to 95% of the plant's protoplasm. It is essential for photosynthesis, the process in which plants make their own food. It is the solvent in which nutrients are carried through into and throughout the plants. And it provides turgidity by which the plants keep itself from proper position. Water has unique properties that promote or enhance a variety of physical, chemical, and biological processes. It participates in many chemical reactions that release and tie up nutrients, create acidity, and wear down minerals in the soil. It influences many of the ecological functions of soils and soil management practices such as water recharge and water loss, air and water balance in the soil pore spaces, rate of change in soil temperature, rate and kind of metabolism of soil organisms, and the capacity of soil to store and provide water for plant growth. Water determines the movement of chemicals and eroded soils to the groundwater, streams, and lakes. Now let's talk about the different classifications of soil water. Naturally occurring soils nearly always contain water as part of their structure. The moisture content of a soil is assumed to be the amount of water within the pore spaces between the soil grains. They can take in water and will keep doing so until they are full, or until the rate at which they can transmit water into and through the pores are exceeded. There are five categories of water surrounding a clay or a soil particle, one of which is the adsorbed water, or also known as the hygroscopic water. So this water is held on the surface of the particle by powerful forces of electrical attraction and virtually in a solid state of very small thickness. It cannot be removed by oven drying at 110 degrees Celsius and may be considered to be part of the solid soil. Another category is the water at permanent wilting point. This water can be removed by oven drying but not by air drying. We also have what we call the capillary water or water at field capacity. This water is held by surface tension and generally removable by air drying, unlike the water at permanent wilting point. We also have the fourth one, which is the gravitational water. This water is removable by drainage and can move in the voids between the soil grains. A flooded field will drain the gravitational water under the influence of gravity until the water's adhesive and cohesive forces resist further drainage and it finally reaches the filled capacity. This kind of water is not of much use to the plant. We also have the fifth one, or the last one, the chemically combined water. This water is in the form of hydration within the crystal structure and not generally removable by oven drying. Now, this is an illustration of the different categories of water. You have for the number one as the adsorbed water. As you can see, the water is adsorbed in the soil particle. For the number two, this is the water at permanent wilting point. For number three, that is the capillary water, the one that is removable by air drying. For number four, you have is the gravitational water that is removable by drainage. And the last one, the fifth one, that is the chemically combined water, the number five, that is already considered part of the crystal structure of the solid particle. So those are the five categories of water. You have the adsorbed or hygroscopic water. You have the water at permanent melting point. You have the water at field capacity. You have gravitational water. And the fifth one is the chemically combined water. Now we move to the qualitative descriptions of soil wetness. The terms used to qualitatively describe soil wetness refer to various stages along a continuum and do not imply that soil water exists in different forms. These qualitative descriptions of soil wetness are widely used in practical soil management and help communicate important facts about soil water behavior. The first one we have is what they call the maximum retentive capacity. When all soil pores are filled with water, the soil is saturated and it is at maximum retentive capacity. Metric potential, or the binding of water to materials such as the soil particles, is close to zero, and the volumetric water content is essentially the same as the total porosity. And at this condition, the soil will remain at maximum retentive capacity as long as water continues to infiltrate, because water held in the pores will percolate downward under the influence of the gravitational forces. So that is for maximum retentive capacity. Now another qualitative description is the FC, or the filled capacity. It is the condition when the moisture content of the soil after gravity has removed all the water it can. And usually it occurs 1 to 3 days after a rain. The smaller pores remain full of water. Many of the intermediate of or the mesopores are partially filled, and most of the large pores are nearly empty. And at this condition, the plants must exert a suction force, usually at 1/3 bar. That is the unit of pressure to obtain water at filled capacity. Another qualitative description that you already have heard earlier is the permanent wilting point, or PWP. This is the soil moisture percentage at which plants cannot obtain enough moisture to continue growing. In this condition, the large and medium pores are completely empty. Water is held very tightly by the mineral and the particles of the soil. Plants exert a suction force of 15 bars in trying to obtain water at this moisture condition. So at this moisture condition, the plants are stressed. And although not yet dead, plants below the wilting point, permanent wilting point, cannot recover even if the water is provided. The last one is the available water storage capacity, or the AWSC. This is the amount of liquid water stored in the soil and subsequently released for use by the plants. This kind of water, it varies directly with the total amount of bedroom size pore spaces, or the mesopores, having a diameter in the range of zero point 0.2 to 10 micrometers, or 0.002 to 0.01 millimeters. The pore space is wider than the 10 micrometers straight water readily, and pore spaces narrower than zero point 0.2 micrometer release the retained water too slowly. And the AWSC, or available water storage capacity, could be calculated by subtracting the amount of water at permanent wilting point to the amount of water at field capacity. Now, this figure illustrates comparisons of soil under saturated soil, or soil at saturation, field capacity, and at wilting point. Saturation is when the soil pores are completely filled up with water. Water at field capacity is when the gravitational water runs down and there is the presence of air. And at wilting points, you can see is when there is almost no moisture or available water for the plants. Okay, now let's take a look how this water moves or flow in soils. Water moves through soil due to the forces of gravity, osmosis, and capillarity. And at 0 to 1/3 bar suction, water moves through soil due to gravity. This is called a saturated flow. And at higher suction, water movement is called unsaturated flow. Water flows through the ground unevenly, called gravity fingers, because of the surface tension between the water particles. Tree roots can also help in water flow in the soil. Tree roots create paths for rainwater flow by breaking through soil, including the clay layers. And once soil is completely wetted, any more water will move downward or percolate, carrying with it clay, humus, and nutrients, primarily the cations, out of the range of plant roots and result in acid soil conditions. And at suctions less than 1/3 bar, water moves in all directions via what we call the unsaturated flow at a rate that is dependent on the square of the diameter of the water-filled pores. The water flow is primarily from coarse textured soil into fine textured soil, and is slowest in fine textured soil such as the water infiltration rates ranges from 0.25 centimeter per hour for high clay soils to 2.5 centimeters per hour for sand and well stabilized and aggregated soil structure. So notice that the water infiltration rate is higher in coarse textured soils than in fine textured soils. Flooding temporarily increases soil permeability, helping recharge the aquifers. There are different factors that can control water infiltration in soils, which are first the soil texture. So, as what I've mentioned earlier, in fine textured soils, water infiltration is relatively slower than the coarse textured soils. And also, water infiltration is affected by the soil structure. For example, fine textured soils with granular structure are more or are most favorable to infiltration of water. And aside from those two, another factor is the amount of organic matter. Having high content of organic matter in mineral soil is good. Coarse matter is best, and if on the surface, it helps in preventing the destruction of the soil structure and the creation of crop. You also have the depth of soil too in previous layers such as the hard pans or the bedrocks. And why is that so? Because infiltration of water is lower in shallow soils than in deep soils. Another factor that can control water infiltration is the amount of water already in the soil. Of course, if the water is, for example, near its saturation point or the soil is near its saturation point, infiltration would be slower. Another is soil temperature. Warm soils take in water faster, while frozen soils may not be able to absorb depending on the type of freezing. Okay, so now let's look on the three main types of forces which contribute to the energy state of soil water. First, what we call the gravitational potential. This is the water potential in which the water has a positive energy and can flow out of the soil through the large pores. And it is a point when cohesive forces are not large enough to hold onto water. And this is significant only when soils are saturated. So that's for the first type of force. Now we have another which is called the osmotic potential. This water potential is due to the attraction that salts have for water through the phenomenon of osmosis. And this is attributable to the presence of solutes in the soil solution. The greater the concentration of solutes, the lower the osmotic potential. And the water flows from the solution with lower solute concentration into the solution with higher solute concentration. This is negative energy relative to free water. So in this illustration, you can see that um, wherever the solute concentration is higher, that is where the direction of water flow is. So solution, uh, from the solution with lower solute concentration, water flows into the solution with higher solute concentration. That is for osmotic potential in the soil. We also have the third one, the last one, what is called matrix potential. This refers to the potential energy of water attracted to soil solids. And this is operational in unsaturated soil above the water table. In unsaturated soil, matrix potential results from the capillarity and adhesion forces or adhesive forces. And plants must overcome the energy of matrix potential to extract water from the soil. Now we are finished with the three main types of forces. Now we move to the soil moisture tension. So what is soil moisture tension? This refers to the tenacity with which soil holds water. So as soil moisture tension increases, the amount of energy exerted by a plant to remove the water from the soil must also increase. So moisture tension is negative pressure and commonly expressed in the units of bars. At field capacity, most soils have um, have a soil moisture tension between 0.05 and 0.33 bars. So there are two forces that allow water to move through the soil, which are the gravitational and the capillary forces. And these two types of forces act simultaneously in soils. Gravity pulls water downward when the water is not held by the capillary action. It influences water in saturated soils, while capillary action involves two types of attractions. We have the adhesion and the cohesion. And capillary forces are greater in small pores than in large pores. For example, in this photo of cohesion and adhesion, we have here is the cohesion of water particles to each other and the adhesion of water to the plant leaves. Now, capillary movement of soil water enables the plant roots to make use of water from water portions of the soil profile, particularly from a water table. Now, the smaller the pores, the higher the water will rise above the water table. As illustrated in this figure, the higher the rise, the tighter the water will be held to soil particles to overcome the force of gravity. So in fine textured soils, it will have higher rise of water or the water will be more tightly held in this kind of soil particles rather than in coarse textured ones. So that's for the soil forces, such as the gravitational forces and the capillary forces that can influence water movement up and down the soil profile. Now we move on to soil water content measurement. So how is soil water content being measured? So there are different methods. First is the hand feel method. This is a faster method, but is prone to error since it requires experience and can be subjective. And if a person has experience in the hand feel method and is comfortable in this method, this is an acceptable method because it will allow for more locations to be sampled because it is not expensive and it's just simple to do just by using your bare hands. Another method is this one is the most common, the gravimetric method. It is a direct measurement of soil water content. In this method, a sample of moist soil is weighed and then dried in an oven at a temperature of 105 degrees Celsius for about 24 hours and finally weighed again. The weight of water loss is equivalent to the soil water content. The formula to determine the soil moisture content is as follows. Wherein moisture content is equal to the fresh weight of the soil minus the oven dry weight of the soil divided by the oven dry weight of the soil multiplied by 100%. We also have the use of electrical resistance blocks. So the electrical resistance block uses small blocks of porous gypsum, nylon, or fiberglass suitably embedded with electrodes. Now, when placed in moist soil, it absorbs water in proportion to the soil moisture content. Now, this equipment is inexpensive and can be used to measure approximate changes in soil moisture during one or more cropping seasons. However, the accuracy and the range of soil moisture contents measured by these devices are limited. So that's all for soil water. Thank you very much for watching. Please like and